In this video, we're going to learn about the binomial distribution, why we need it, where we can use it, what is the formula for this distribution, how to use the formula. So without any further ado, let's start this. We want to start by having a bit of intuition about the binomial distribution. So we'll start by looking at this simple experiment of tossing a biased coin once. We have only two outcomes, which are head and tail. Let's say the probability of getting a head is 2 by 3, which would give us the probability of getting a tail as 1 by 3. And we would like to represent this information in a probability distribution table as such, where x is the discrete random variable of number of heads seen. So x can assume a value of 0 or 1, which means we can have 0 head or 1 head, which makes complete sense. Then we move on to level 2 of our experiment, and we are tossing our biased coin 2 times and looking at all the possible outcomes which we can have. We'll see later how this is going to help us in developing an intuition about the binomial distribution. The probability of getting a head is still 2 by 3 for the first toss, as well as for the second toss. This means that having a head on the second toss is independent of having a head on the first toss. So we have 4 outcomes in total, and we can find the probability of each outcome as such. And if we want to represent this probabilities in a probability distribution table, we have to add these 2 probabilities, or we can just multiply one of the probability by 2, as both of the probabilities are the same. Again, our discrete random variable is the number of the heads seen, which can assume the value of 0, 1, or 2. Let's move on to the third phase of our simple experiment, and we are tossing our biased coin 3 times now and looking at all the possible outcomes which we can have. The probability of getting a head is still 2 by 3 for the first toss, as well as for the second toss, as well as for the third toss. Although we are not going to write the probabilities for the third toss, so as not to make it more messy than it already is. So the outcome of all the 3 tosses are independent of each other. We have 8 outcomes in total, and we can find the probability of each outcome as such. You should pause the video and make sure you understand how we got these probabilities before proceeding further. And as you can see, we don't have enough space left, so we are now only going to look at the outcomes portion of the tree diagram. So here we have the outcome portion of the same tree diagram. In order to make a probability distribution table, we need to add some of these probabilities. So we need to add these 3 probabilities to get the probability of having 2 heads. Again, instead of adding, we can just multiply by 3, as all the 3 probabilities are the same for this option as well as for this option. Similarly, for probability of getting 3 heads and probability of getting 0 heads. And now we can make our probability distribution table, but this time we want to further manipulate the expression for our probabilities by observing a pattern. So probability of 3H can be written like this. Similarly, probability of 2H and also the other two probabilities. Pause the video and make sure that you understand how we ended up with these expressions before proceeding any further. So now we move to the level 4 of our simple experiment, which looks like anything but simple now. And we are tossing our biased coin 4 times. Again, we are not going to put the probabilities on the branches, so it's not too complicated more than it already is. But the probability of having a head is still 2 by 3, and probability of having a tail is still 1 by 3 for all the tosses. We can find the probability of each of the outcome as such. Pause the video and make sure that you understand how we got these probabilities before proceeding any further. And no wonder we don't have enough space, so we move on to the next page. So here I took the same probabilities and we try to color code these probabilities so as to make it easier for us. So probability of getting 3H would be this, and probability of getting 1H would be this, and so on. Again, instead of adding, we are multiplying by the relevant number. Further manipulation of the expressions for our probabilities would give us this. Pause the video and make sure that you understand how we ended up with these expressions before proceeding any further. So the big question is, where are we going with all of this? Let's look at the result from our simple experiment from another perspective. So I can write all the probabilities for the 4 tosses as such, and all the probabilities for 3 tosses as such. And although we did not formulate the expression for the 2 tosses and 1 toss, but we can still write the probabilities in the same way. And now, just removing the notation for the probability, we have a much clearer picture of the whole situation, and this seems pretty familiar for some of you, those who have studied about Pascal's triangle. The numbers in red, they make up the Pascal triangle. Pause the video and make sure you see the Pascal triangle. Now we want to find out a formula for the nth term of this pattern. So we don't have to do another simple experiment for 5 tosses or 10 tosses or worse, 100 tosses. The formula for the nth pattern comes out to be this, where n is the number of the tosses and r is the number of heads for our experiment. Pause the video and make sure you understand how we ended up with this nth term formula for our simple experiment. Now we would like to formulate a general expression from this nth term formula. So we proceed as this, and then by assuming P equal to probability of success, which in our experiment was the probability of head, and Q equals to probability of failure, which in our experiment was the probability of tail, we can get the general form of the formula, where NCR is the combination of R objects from N objects. In some textbook, it is written in this format, where PR is the probability of selecting R objects and Q equals 1 minus P. Now this is the formal way to write the formula, which would give us the binomial distribution. The binomial distribution itself, however, is denoted as this, which we read as the discrete random variable x has the binomial distribution with n number of trials and p probability of success. Pause the video and make sure you understand these notations. Then another big question: when can you use binomial distribution? It turns out we can use this formula in very specific ways. So first, if you are conducting trials on a random sample of a certain size denoted by n, which means we have a finite number of samples or trials. Second, there are just two possible outcomes in this case in our experiment, that is head and tail, and these are often referred to as success and failure, although we can use a neat little trick in some cases where we have more than two possible outcomes. Third is both outcomes have fixed probabilities, the two probabilities adding to 1. The probability of success is usually called P, that of failure Q, so P plus Q should be equal to 1. The probability of success in any trial is independent of the outcome of the previous trial. Only if all of these criteria are met, we can assume the distribution to be binomial. So now we will look at some questions and we will apply our newly learned knowledge to solve these questions. So this is the formula for the binomial distribution we have already seen before. So the question is, a fair coin is tossed 20 times, find the probability of having 6 heads. So I want to find how many times I would have. So I want to find the probability of having 6 heads, which means n is 20 because I'm tossing the coin 20 times. R is 6 because I'm interested in having 6 heads. The probability of success is 0.5, which means that this coin is fair. So just plugging in these numbers into the formula, you will get the answer, which is 0.0370. And similarly, if a fair coin is tossed 20 times and we have to find the probability of having 6 tails, we can again use the same formula, and this time also all the values are the same because this coin is a fair coin and the probability of head is the same as probability of tail, and no wonder we get the same answer. Let's look at another question. A biased coin is tossed 20 times. Find the probability of having it 6 heads if the probability of head is 2/3. So again, using our formula, n is 20, r is 6 because we have 6 heads here. P is 2 by 3 in this case because this is a biased coin. And plugging in the values in the formula, the answer is 0.000711. And similarly, for the tails, we can again use the same formulas, but remember in this case P is 1 by 3 because we are interested in having 6 tails. And plugging in the values, we get 0.182. And in this case, it's obviously not the same probability because this is a biased coin. And the last question which we will solve is this. So in rock, paper, scissors, if you guess entirely at random, what is the probability that you are right exactly 5 times out of 15? So first thing, we have 3 options, not 2 options, but we can use our little trick to make 2 options out of these options, because we are interested in only the right answer or right guess or a wrong guess. So for a guess to be right, out of 3, the probability should be 1 by 3. And the other 2 would be the wrong guesses. So in this case, I have to guess what is the probability that you are right exactly 5 times out of 15. So n is 15, r is 5, p is 1 by 3. Just plugging in these values, our answer is 0.214. Hopefully you understand the video and the concept explained in it, and you will apply during your exercises.